Hello everybody, my name is Mary Grace Carr and this is my Physics 2211 Lab 4 Oscillations. So before we start today, I just want to give a brief overview of the concepts that we will be covering. Today we'll be analyzing the motion of a spring mass system swinging in an arc and oscillating on the spring. We will be utilizing the momentum principle and the energy principle within our experiments. After running our experiment through Tracker, we will then use the data to calculate the spring force, period of oscillation, and L0. Next, these values will be implemented into a GlowScript code to create a computational model, which will then be used to analyze and compare to the experimental values. Lastly, we'll go over any conclusions or any questions to be answered. Overall, the goal of this lab is to create a model of the motion of a mass on an oscillating string. This will be done by a comparative analysis between the graphs of motion and energy, and will mainly focus on the difference of predicted motion versus actual motion, and the change of kinetic energy, the change of gravitational energy, and the change of spring force potential energy. We will continue the use of Newton's second law in this experiment, which is force is equal to mass times acceleration. Like I mentioned before, the two principles utilized in this lab are the momentum principle and the energy principle. The momentum principle is implemented in order to use the velocity and the position update formulas. The energy principle is the main principle for this lab, as it defines what we will incorporate into our system, which is the change in kinetic energy, the change in gravitational energy, and the change in potential energy, which is set to equal the total change in energy. This change in energy should be equal to 0 because of our definition of the system, which is to include spring, the mass, and the earth. The initial conditions listed at the top right of the screen were found from the tracker data. The initial position vector originated from the first x and y entry of the first time frame in tracker, and the initial velocity vector is 0 because the mass is initially at rest. So now if we hop into tracker, we can see our experimental system operating. I'm just going to play it for a little bit, and you can see our mass system oscillating. And over here on the right, we can see our outputs, x and y, and our time, as well as our graphs, which show these oscillation periods. We can also see where our axes are and where our calibration stick is, which shows that it is about 0.7 meters from the top to where the center of our spring is. So now that we've gathered our experimental data from Tracker, we can now create some calculations from it. The period of oscillation is calculated by t is equal to 2 pi times the square root of mass divided by the spring constant k. But since k is unknown, I followed the example video of using 3 full oscillation periods to get an average, which turned out to be 1.587 seconds. From here, I then calculated the spring constant k, which came to be 6.83 Newton meters. And I calculated this by this equation right here on the screen. Lastly, I had to calculate L0, which is calculated by the absolute value of L minus mass times g divided by the spring constant k. This equation calculates our stretch length. L is equal to 0.7 meters and m is equal to 0.402 kilograms. And this gives us an L0 value of 0.123 meters. And then here we can look at our GlowScript code where we have our initial values. So here we have our initial value of our system mass, as well as our position and velocity vectors that we discussed earlier. And then we have our g constant, our spring constant, as well as our relaxed length of the spring, which we just calculated. And down here we have our fundamental equations for energy, as well as our equations to find L in our GlowScript code. So in this block of code, we define our initial energies, which are equal to the final energies to make our energy principle true, as well as our forces and our application of the momentum principle. And then lastly, we have our calculations for all the different types of energies. So when we go to run our code, we can view the model. In order to run this, we had to take our CSV file from the tracker data and then upload that into GlowScript. So viewing the model, we can see that the red ball represents our experimental data, while the blue ball attached to the spring is our computational model. They closely mirror each other, but we can see the discrepancies when we take a look at the graphs down here. So here's a closer look at the x and y position versus time graphs that display the discrepancies between the computational model and the experimental model. The periods of oscillations are nearly identical, yet there's a shift and a shrink in the experimental graph compared to the computational model. Although it is nearly impossible to match them perfectly, these differences can be attributed to human error and mistakes in the recording and extraction of the data in Tracker. So now we can go into our analysis and conclusion. So for our first question, is the energy principle satisfied? The answer to this is yes. This can be observed in the model on the right, as the orange line, which represents delta E, represents the change in energy over time, and this is equal to 0. This indicates that no energy was gained or lost in the system, but rather just transformed into different types. In this experiment, our system is defined as the spring mass in the Earth. So for our next question, where we compare the period for the x component and the y component, we can see where we estimated t, which is the period of oscillation. So for x, I calculated it to be 1.67 seconds, while for y, which is what we used in this video, was 1.587 seconds. So these two time periods are different for the different components, and this can be contributed to the fact that the y period is most affected by the stiffness of the mass, while the x period is more affected by gravity and length as it moves as a pendulum. Judging from these two measurements, it can be concluded that the mass does not in fact move in a perfect circle.